So before we get into synthesis, let's first talk about what sound is at a very high level. You can think of a sound as being composed of multiple different sine waves. So you have one sine wave, which is the fundamental, and that's typically the frequency that you perceive. And then you can have multiple different sine waves at lower volumes, higher up in the frequency range. And these are called overtones. And there's a subset of that called harmonics, which are integer value multiples of that sine wave. Anyways, this sounds kind of geeky, but all this to say is that when you hear terms like harmonically rich or harmonic content, you're basically describing the density of a sound, I guess, and the richness. So you can think of a sine, when you hear a sine wave, it's kind of a pure, almost like a flute, very pure, soft sound. And anything more complex with that usually involves multiple harmonics. And this is an important concept to keep in mind, so remember that when we get back to talking about synthesis. And that also brings up another word, which is timbre. And that's basically the perceived characteristic of a sound. So you can think of the different harmonics of a sound contributing to a different timbre. And the best way to think about this is, how do you tell the difference, for example, between a trumpet and a cello, or a trombone, or the human voice? And if they all play the same note, we're still able to tell them apart. And that's via the difference in timbre, which again goes back to the harmonics. So they all have the same fundamental frequency, but they may have different harmonic content. So they have different sets of overtones and harmonics that contribute to their perceived sound, even though the perceived frequency can remain the same across them. So that's sound at a really high level. And obviously there's kind of the physical definition of sound, which is vibrations and changes in pressure in the air. But for our purposes, we're just going to think of these multiple different sine waves per sound. You have your fundamental and some varying degree of harmonics at different levels. The other word that you're going to hear a lot is the word modulation. And this may sound complicated, but just think of modulation as change of some parameter by some other parameter. So as long as I change something and that change is contributed by some other thing, we can say that we're modulating instead of, so you can most of the time substitute the word modulation for the word change. So for example, the letters FM are very common, and that just stands for frequency modulation. So you can just think of that as a change in frequency. All right, that's it for the kind of basic terminology. We have sound, we have harmonics, and we have modulation and timbre. So let's move on to talk about subtractive synthesis at its very basic level. So we have two words, subtractive and synthesis. So we can kind of split these up and talk about them separately. First, let's talk about synthesis. So the basic of synthesis is just to synthesize, is to create sound. So sound can basically be anything, but for our purposes of kind of typical synthesizer sounds, what we're really looking for is to change the timbre of the sound over time. And it's basically that concept for regardless of what kind of synthesis you're using. So we're going to be talking about subtractive synthesis, which is probably the most popular and simplest one to understand. But really, any synthesis type you think of, you will always at some point be changing the timbre of the sound. And one thing I forgot to mention about the timbre is it's not just the harmonic content of the sound, it's also the kind of amplitude envelope. And we'll cover what envelopes mean, but it's not enough to kind of describe the sound as purely what it sounds like at full volume. It's also helpful to distinguish timbre by the way the amplitude or the volume changes over time. So for example, if you strike a mallet on a xylophone, for example, that'll have a really quick attack versus kind of bowing a cello really slowly. You can ramp up the attack over time, and that also contributes to our perceived notion of what the sound actually is. And that's kind of how you tell the difference between a cello and a xylophone, amongst other things. So anyways, going back to the basics. So synthesis, just think of as changing timbre over time, and a timbre being defined as the characteristic of a sound defined by its harmonic content or its set of frequencies, as well as the amplitude envelope. And if you don't know what amplitude is, just think of the volume of the sound, basically. So that's the kind of 40,000 foot view of what synthesis is in general. So let's talk about the other component of subtractive synthesis, the word subtractive. So in this case, subtractive refers to the harmonic content of a sound again, and that's why it's important to understand the kind of general idea of what harmonics are. Is that for subtractive synthesis, we're starting with a dense array of harmonics, so lots of little sine waves, and then we want to remove those over time, so we're subtracting from that rich sound from the beginning. And that's at a really high level what subtractive means. And at the same time, you can have an intuition for what additive synthesis is, where you start with really simple sounds with simple harmonics, for example, pure sine waves, and you just add them together to create a sound rich in harmonics. And again, it's really helpful, I'm going to reemphasize this, that for most of these synthesis types, we're really just shaping the timbre of the sound. So whether you're adding harmonics, removing harmonics, changing harmonics, at the end of the day, you're just kind of changing the characteristic of the sound over time to create something interesting and pleasing to hear. So now that we covered those basic terms and subtractive synthesis at a super high level, let's talk about what the general basic building blocks are in a typical subtractive synth. So you can think of the three core components as the oscillator, the filter, and an amplifier. So an oscillator is what generates the sound. It oscillates some kind of waveform, either a sine wave or a sawtooth wave or triangle or square or whatever. And it repeats it over time, and that produces a steady pitch. And that's our main sound source. And this is where you typically in subtractive synthesizers, you would start with certain waveforms which have a lot of harmonics. So you wouldn't start with a sine wave typically because you have only one harmonic or only one fundamental frequency. So you don't have much content to remove with the filter. So it's less interesting that way. So typically you would start with something like a sine wave, or sorry, with a saw wave, which would have a lot of harmonics in addition to the fundamental, which gives you this really rich sound from which you can sculpt. So another way to think of subtractive synthesis is like sculpture in art. You start off with a giant piece of rock, and then you're kind of removing from that in order to create something interesting. So the next component after the oscillator, which produces the sound, is a filter, and a filter removes frequencies basically. So you have different kinds of filters. You may have heard of things like low pass filter, high pass filter, band pass filter. And the low, high, and band, and mid, and all that refers to the frequency range. So when you hear low pass filter, you're passing low frequencies. It's as simple as that. So you would start with your fundamental at some frequencies, plus some harmonics at higher frequencies. And then with a low pass filter, you're given some range, you're removing frequencies that are higher than that range and leaving frequencies intact at lower ranges. And the point at which this happens is referred to as a cutoff frequency. So you may have seen a cutoff frequency knob on a synth, which is usually one of the more popular or usually the bigger knobs because it contributes the most to it contributes the most to the character of the sound, especially in kind of classic subtractive synthesizers. Like the Moog filter is a really kind of a main stage in subtractive synths. And that's it for the filter. After the filter, we go through an amplifier, and typically we use a voltage controlled amplifier, but we'll get into that later. You can think of an amplifier as basically something that just changes the volume of the sound. So if you remember timbre as being a combination of the harmonic content plus the volume of the sound over time, then the harmonic content is determined by the oscillator and the filter. Again, we start with lots of harmonics, and the filter removes some of those harmonics. And finally, we go through the amplifier, which changes the volume. With these three building blocks, we basically have a way to shape the timbre of the sound over time, which in my definition of synthesis, and others can disagree with this, but we're changing the timbre over time, basically, in any kind of synthesis. In a subtractive case, these three building blocks give us the core of what we want to achieve. All right, so that covers the three basic building blocks of subtractive synthesis and kind of a high-level view of how they contribute to the change of the timbre. The other thing I wanted to mention is it's important to note that there are two general categories of signals when we're dealing with synthesizers. of any kind really, but especially in a modular sense, these signals become more exposed and more obvious because you actually see the cable that corresponds to that signal. Whereas in more traditional fixed architecture sense, a lot of this gets abstracted away. And that's why I think it's really important to at least have some kind of practice or experience with modulars. You don't have to go crazy, but it really makes the connections obvious between the different modules, and it accentuates your knowledge and forces you to actually learn what's going on. So it's applicable then, even if you go back to fixed architecture sense, you'll still have a much better grasp of how things interact. And so you'll have an easier time synthesizing sounds that you hear because you'll know exactly what's going on. So anyways, back to what I was saying, you can think of two types of primary signals. You have audio and control. And what I mean is that in the audio side, it's what you're hearing basically. So it's what we've been talking about so far. You have an oscillator that produces a sound. It goes through a filter. It alters the characteristic of the sound. And then the amplifier changes the volume. So this has been kind of the audio signal path throughout. And that's what you typically interface with. And that's typically the outputs you would see on a traditional synth. But the other type of signal, which is just as important, is what I would kind of classify as control signals in general. And then within those, you have control voltage, you can have gate triggers. And I say voltage in this case because we're dealing with analog synths, but really control could be digital signals if you're in a digital synth. But the general concept is control signals aren't audible. You're not going to hear them. You're just using them to control other parameters. And parameters can be anything. So for example, let's say you have an oscillator. One typical parameter you would have is to change the frequency, the pitch of the sound, right? So one way you can do that is to change a physical knob on a user interface. So you would rotate a knob to control the frequency of the synth. But the other way to do it is to have that change be automated. And that's where you rely on control signals. So you can rely on basically anything can generate a control signal. You can have the keyboard generate control signal. You can have an LFO, an envelope, and we'll cover all these later. But the general idea is that there's a class of modules that deal with generating control, and there's a class of modules that deal with generating or processing audio. And this is important because if you remember, my definition of synthesis is change of timbre over time. So in order to change something over time, which I guess is kind of redundant because change implies time, but basically you want to be able to alter the shape and the structure of the sound, so both its harmonic content and its volume, over time in a pleasing way. And you don't want to have to rely on your hands to do everything. So that's where control signals come into play, because you can allow the machine to do it for you. So it could be a repetitive motion, it could be a sequencer, it could be an LFO, an envelope, and all kinds of different ways. You can even use audio to use as control signals, but we're not going to get into that for now. So for this tutorial, I guess just think of audio as separate from control. Audio, you can hear it, and it's the sound that's going through the synth. And then control kind of happens on the side and is used to control different parameters automatically for you, or via user interface. So it could be manually by a knob or a slider or something, or it can be automated by the system. All right, that's a lot of talking. Hopefully all of that made sense. If you have any questions, ask in the comments. So enough theory and talking. Let's see what this actually looks like on a synth. So right here in front of me, I have this Kilpatrick Audio Phenol synth. So basically the stuff I'm talking about is applicable to Eurorack, 5U, even fixed architecture synths. I'm going to try to keep everything I say super generic and not specific to this particular piece of kit. But I'm going to use this as an example because this is a great little unit for demonstrating these concepts. Because in effect, it's a modular system, but it's not truly modular in the sense that you can't swap out the modules, but it's modular in the sense that you have these modules effectively here, which aren't actually connected. So you have to do all the connections yourself. So it's effectively like a Eurorack system, but the modules are hardwired, or not hardwired, but are fixed in the panel. So what is a module? Basically, it's a self-contained, independent thing. So that sounds kind of generic because it is in a way. A module could be anything, but you can think of it as a black box that has inputs and outputs and some control like knobs or physical controls. And modules can do anything. They can either be purely in the audio domain, so they can just process audio or create audio. So it could be like a reverb, an oscillator, a filter, or they can deal with purely control signals. So it could be an LFO or a CV mixer or whatever. Or it can be both. Some accept CVs into audio inputs and vice versa. And some have combinations of everything. And some oscillators can go in the low frequency range, so they turn into LFOs. And you can use an oscillator and audio rate also as control signal. But again, we're not going to cover that here. We're just going to keep it simple. So here, you can think of the modules, or not think of them. They are literally this. Basically, everything with a black bar on top of it is a standalone module here. So as you can see, I have 2 oscillators. I have 2 filters, 2 VCAs, 2 envelopes, an LFO, an adder divider, a MIDI CV to converter, and a mixer. So there's a handful of modules here. And typically in a Eurorack system, each of these will be its own physically separate module that you would plug into a system. So modules are basically independent of each other, and it's up to you to interconnect them in whatever way makes sense to you. So what we're going to do is we're going to build a patch from scratch using really, really simple procedures so that you can sort of understand what each step does and what each patch cable does at any given time. And that's an important thing to know, because oftentimes you can get intimidated by seeing these wall-high modular mega systems with billions of patch cables all over the place, and it looks like a giant science lab. But at the end of the day, if you remember the core concepts, every individual connection serves a very particular small purpose, and then you're just kind of building all of these over time. So it seems complex when you look at a finished patch, but every connection was ideally created intentionally with purpose. Okay, so let's start off by just producing a simple sound just so we hear something. So in my oscillator section here, as you can see, I have some outputs, and it outputs different waves at different jacks here. So I'm going to grab, for example, the triangle wave. And I'm going to plug it into the mixer here. And basically this goes straight to my speakers you can think of. Just going to lower the volume. So now we have a steady pitch coming out. And there's a coarse pitch knob here that I can change the frequency with. And that's basically it. That's the world's simplest synthesizer patch. We have a sound coming out. We just plugged in the output of the oscillator into here. And again, that's another thing to remember, especially if you're used to fixed architecture synths. You really have to think of these modules as really bare bones and dumb and standalone. They do one thing well, but they're completely clueless as to the external context of what you're trying to achieve. So all the oscillator's doing is producing a steady frequency at a max volume at all times. It's not doing anything else. It doesn't know anything about your keyboard playing. It doesn't know anything about the filters or anything like that. So basically there's a constant sound coming out of here at all times. I mean, not literally, but there's a signal representing a constant sound. So if I plug it into the mixer, I'm hearing that constant sound. And here I'm adjusting the volume with the mixer. But if I didn't have a mixer, if I plugged it straight into a speaker, I'd probably blow the speaker. It would be just a max volume, constant pitch going on. So how do we make that interesting? Let's first switch it to a ramp wave or a sawtooth wave. So now we have the ideal wave for the basis of a subtractive synth patch, which is a sound that is rich in harmonics, and you can hear it. It's really thick and buzzy. It's really full and meaty. So one way to alter the timbre of the sound, or at least the harmonic content portion of the timbre, is to filter some of those harmonics out. So remember, we have a fundamental frequency here plus a bunch of other sine wave frequencies on top of that. And we can remove some of those higher harmonics with a low pass filter, because again, we're passing the low frequencies, but we're removing the high frequencies, which is where most of those harmonics live. So to do that, I'm going to run into this low pass filter module. And again, this is just a dumb, simple module. It doesn't know anything about the rest of the synth. It doesn't know anything about music. All it's doing is it's removing frequencies from a signal that comes in. So it's up to you to figure out what to do with that. And again, if you remember a module just being a black box with inputs and outputs, here we have an input. So again, I'm only dealing with audio signals here. So I have an output of my oscillator into the input of my filter. It's going through a black box, processing some audio, and it's coming out of here. So now I'm going to grab another patch cable. So now the output of the filter, I'm going to feed in so we can hear it. And now you can hear if you remember, what I'm changing here is the cutoff frequency. So if you remember, the cutoff frequency is generally the point where the effect of the filter happens. I guess you can think of it that way. So in this case, it's a low pass filter. So anything below the cutoff frequency will remain intact. Anything above it will be attenuated effectively. And there are different types of filters. There are different slopes, different characteristics. That's why you hear things like a Moog filter or a TB303 filter or a Oberheim filter. They each have their own tonal characteristics that contribute a lot to what you're hearing, to the sound. And that's why you would see people purchase lots of different types of filters, because each one has its own sonic characteristic. And the more you have, the more you can kind of alter the palette of a sound and keep things interesting. All right, so what we've achieved now, we have the first building block, the oscillator, the second building block, the filter, and if you remember, the third building block was the amplifier. So right now, the main thing that's missing is our volume control, the amplifier part. And we have this voltage controlled amplifier here. And that's basically, you can think of it as just a volume knob that you can control with control signals. So if you remember this mixer here, I have a level knob here. So in theory, I don't need this VCA. I can just change my volume here and I'm good to go, right? Well, the problem with this is that I can't actually control this knob with control signals, which we'll see is really useful later. So if I'm just going to control it with my hand, then I might as well just plug it in here. But we're going to use the VCA to follow the traditional path and ignore that this knob exists. Again, a VCA is just a black box with an input and output. So we're just following a signal path. I'm going oscillator through the filter input, output of the filter, into the input of the VCA, and then I'm going to come out of the output of the VCA here. And now I have a volume knob here. So now we have all the mechanisms that we need to alter the timbre of the sound in, albeit a basic way here, but still the fundamentals are there. We have the way to shape the harmonic content of a sound. So we start with a rich sound. We filter it out to remove some of that richness. And then we go through the amplifier to change the volume of the sound. So we have volume change and we have frequency content change. And that's enough to keep the sound interesting, and it's a pretty basic patch. So this is fine for what we call a drone patch, and a drone patch is typically something that doesn't require human input. It typically preserves a single frequency, and things kind of evolve over time purely by the machine. But most of the time we want to be able to perform something or have it be musical. And typically you would either use a sequencer for that, which is just a series of different musical notes that you can apply that repeat over time. Or you can use something more traditional like a black and white keyboard, which is common in East Coast synthesis. Or you can use more esoteric things like touchpads and ribbon cables and theremin style inputs. Basically, you can do anything, but for now, we're just going to use a standard MIDI keyboard. So you can't see it on screen, but I've plugged in a MIDI keyboard here, so just trust that that is what's happening off screen. So for the purposes of this demonstration, the fact that it's a MIDI keyboard is kind of irrelevant. So just assume that we're getting some kind of gate and CV signal that produces pitch. And that's coming from this module here. There's something called a MIDI to CV converter. It just takes MIDI signal, which is just a digital signal, and it'll convert it into gate and pitch, which is the two most common, or I guess the only two ways to indicate control from a black and white keyboard. So we mentioned gate briefly before when I mentioned the three main types of control signals, CV, gate, and trigger. So it's worth describing gate a little bit here. A gate is basically two levels of voltage that alter. So it's either on or off, you can think of. It's almost a binary signal. In a gate, it usually goes high for a certain amount of time and then low for another period of time. Usually it's low by default. So in the context of a keyboard, for example, when I push down on a key, that'll set the gate high for as long as the key is down. And when I let go of the gate, or when I let go of the key, the gate will go low again. This is just another type of control signal where normally when you hear CV or control voltage, it's a smooth range of voltages. So it could be anywhere from 0 to whatever, 5 volts, I guess. Whereas a gate is either 0 or 5 if we're using a 5-volt system. And so with the combination of these two, we can basically translate what is happening on the keyboard. So with the gate, we know when my finger is down or up. And with the pitch output here, then we know what key I played. And this is two very crude kind of basic pieces of information that we need to determine what I'm playing on the keyboard. Obviously, we're missing things like velocity, aftertouch, pressure, and all that. But this is the most fundamental basic way to translate a black and white keyboard into signals that we can use here to make it control something musical. And the other thing to mention about this pitch output here, I talked about CV as being just a continuous range between two voltages, but a pitch usually follows some kind of convention, and the most common convention is called volt per octave, which basically means that for every octave of notes, there's a 1 volt range there. And that's just a convention that we use to be able to track the different divisions, musical divisions on a keyboard, and to map them to frequencies so that you actually hear the kind of Western music scale as you play on a black and white keyboard. And that's what's being outputted here, and that's what the oscillator accepts here in this pitch input. And that's basically the difference between FM input and pitch input, is that one of them tracks pitch using this 5 volt or volt per octave convention, and the other one is just the linear or exponential. I'm not sure what's happening here. But anyways, I digress. Details. For now, I'm just going to put in a pitch output from my MIDI keyboard, essentially, and feed it into the pitch input of the oscillator. So if I bring up the volume. So now you can't see off screen, but I'm going to be playing some notes on the keyboard. And as you can hear, as I play along the keyboard, I'm getting the musical notes playing on the oscillator right now. So that's one piece of the equation. The other piece of the equation is volume, because right now if I raise it up, we have a constant sound, which obviously doesn't map to how I'm playing, because even if I'm not holding any keys on the keyboard, you're still always going to hear this sound coming out. So we need a way to translate me pushing the key down on the keyboard into the volume changing here, because that's typically what you'd want, for example, on a piano. When you don't play anything, you don't hear anything, and then when you push a note, the volume goes up and then back down. So the most simplest way to do this is to feed my gate signal, which you remember is just a choice between two voltages, either off or on. So I can feed that into my amplifier. So the amplifier has an amp in here, and that's the advantage of the voltage controlled amplifier versus just using the mixer knob here, is now I have a control here. Remember control voltages. I have a way to control the volume of the sound using some other voltage. In this case, I'm going to use the gate output. So whenever the voltage goes high here, so whenever I push a key down on the keyboard, it'll completely open the amplifier, so it'll make it loud. And when I let go of the key, it'll go to 0, which will make the amplifier 0, and then it'll silence the sound. And you can't see what I'm doing off screen, but I'm playing notes on the keyboard now. And as you can see, we don't have that sound constantly playing now. It's only playing when I push down on a key. So the other step now is to make the volume change more musical and interesting. So if you remember when we talked about timbre, we mentioned it's a change in harmonic content as well as an amp envelope. And I mentioned I was get back to what an envelope is. So you can think of an envelope as just a change in voltage over time, I guess. But more specifically, typically you have something called an envelope generator, which is controlled by a gate signal. So remember, the gate is just two values on off. So what an envelope generator does is it creates a shape that is triggered by this gate. So instead of having just abrupt on off, which I have now, so now I push a key down, full volume, I let go, goes off instantly. So if you remember, for example, differentiating between a trumpet and a cello or xylophone, they all have different characteristics of how the volume changes over time when the instrument is played. So for example, if you have a slow rising cello sound, you typically want the volume when you activate it. For example, if you were going to play it on the keyboard, if I push a key down and I'm trying to simulate a cello patch, I would want the volume of that cello to rise slowly over time, even though I'm pushing the key already, instead of abruptly going on like this. So the way to do that is with the envelope generator, which you can think of as it translates a on-off signal into a smooth signal. And it has different stages typically, so I don't want to go too deep into this because there are different kinds of envelope generators, but you may have heard the term ADSR, attack, decay, sustain, release. And this is just one type of envelope generator which characterizes how the sound or how the control voltage changes over time as it goes through different stages while the gate signal is high. So normally on a fixed architecture synth, you're probably used to thinking of the envelope generator as something that is implicitly tied to the keyboard. So you play a keyboard and then you have the kind of high attack, which creates a pad sound, or quick attack, which creates a plucky sound or whatever. But I think it's important to kind of disconnect that knowledge and disassociate the envelope generator with the keyboard. Again, an envelope generator is just like any other module. It's a black box with inputs and outputs. It just happens to have an input as a gate and an output as a control voltage. And we typically think of it as changing the volume of the sound when you play a keyboard, but conceptually it could be anything. It just receives some trigger voltage and outputs another smooth voltage. What you feed into the input and what you feed in from the output of that is completely up to you. And this is kind of the mental shift you have to make when you get into modular, is that all of a sudden these concepts that have been ingrained in you from fixed architecture synths now open up a completely different possibility and a completely different world. So the most typical thing would be for me to feed my keyboard gate here and then use the output of the envelope generator to change the volume of my sound over time. And I'm going to patch that in now just to demonstrate the basic concept. So again, now currently I have my gate going directly into the amplitude change, or into the VCA. But since I don't want an abrupt sound, for example, let's say I want a slow attack, then I would feed my gate into the envelope generator. And what that's going to do is going to tell it to start going through its different phases. In this case, I believe we just have a simple attack, decay, release. We don't have a 4-stage envelope generator. So again, my gate is coming in here. It's triggering it. All it's doing is producing some control voltage. So again, it's just some shape of voltage going up and down. What you do with that signal is completely up to you. In this case, I'm going to feed that into my VCA because I want it to control the volume of the sound. And now I can use these two shapes here to alter the shape of the envelope. So I have an attack and a decay release here. And again, you can't see off screen, but I'm pressing a key on the keyboard. And now instead of going instantly on and instantly off when I release, as I hold down the key, the voltage rises slowly. And that voltage is used to control the amplitude or the volume of the sound. So we get something a little more like a cello now. And that would be your most standard patch for creating a basic instrument type sound. But again, I want to emphasize that even though this is the common way to do it, it's definitely not the only way. And if you start to kind of free your mind and start thinking about control voltages as just signals that can change other signals, it really opens up a whole different world. So basically anything that you can... Another interesting way, I guess, to think about control voltage is just like another hand, right? So for example, here I have a bunch of knobs. So I can start tweaking these knobs by myself. But most of the time, at least on a well-designed module, you would have a control voltage input that corresponds to the function that you can do with the knob as well. And you can start to think of control voltages as just assisting, as just providing another hand for you to change things, either systematically or like periodically, or via some other human control device like a pressure patch panel or something, or a pressure panel. So really that's where the beauty of modular comes in, is that now you can start to experiment with what would happen if I feed this envelope generator output into the pulse width modulation or whatever. I mean, this is a pretty simple set of modules here, but you can now understand why there's all these esoteric weird modules and why people collect a ton of modules, is that the possibility for types of change you can produce to the sound goes up exponentially. And again, remember, synthesis is just a change of timbre over time. So any way you can alter the timbre over time could make the sound more interesting. And there's tons of different ways to do that. We're not going to cover that in this basic video, but I just want you to sort of think of, kind of disconnect your mind from the traditional way of patching and understand the core concepts, which are pretty basic if you think about it. And then apply those core concepts to more weird modules and start patching things in completely different ways. And at least that for me was the most helpful kind of mind shift when it finally clicked for me that there's audio signals and control signals, and you can basically alter what a sound sounds like over time in so many different ways. And that's where it kind of gets interesting, at least in my view. So anyways, I guess we can move on here. We have an LFO. We'll just cover that for completeness sake. And what that stands for is a low frequency oscillator. And that's literally what it is. It's an oscillator that oscillates at frequencies below hearing range typically. So you can't actually hear this wave, but you can use it as a control signal for other things. And this is really typical. This would be your kind of simple repetitive wave that you can use for things like vibrato, tremolo, or any other effect. So for example, we have a sine wave coming out of this LFO here, and I'm just going to feed that into my cutoff frequency input of my low pass filter. So again, I can do this with my hand, but why waste my energy if I can just have a robot do it for me? So I feed this sine wave output. And the input there is called FM in. And again, this could seem kind of daunting at the beginning, but if you remember the basic definitions and you just translate the words, FM just means frequency modulation. If you remember, modulation just means change of some signal with some other signal. In this case, the frequency. And the frequency here refers to the cutoff frequency of the filter. And remember, that's the point where the filter has its main effect. So effectively, this input just means change the cutoff frequency for me given this other signal. And in this case, that other signal is just a sine wave. And a sine wave just goes up and down, up and down, up and down. So really what we're going to do is we're just going to change the cutoff frequency up and down, which just means you can think of it as just where some automatic voltage will change this knob for us. And again, there's an FM input here, so you can adjust the amount that this voltage has an effect on the cutoff frequency. And then I have a speed of an LFO here. And you can already start to imagine how this can grow exponentially more complex, especially if you start using more involved modules. For example, here we have a very primitive LFO, but you can imagine an LFO module which has an input, a control input for the speed. So if I do this with my hand, imagine I can do that with another LFO or a sequencer or an envelope generator or anything that creates control voltages. Then you can potentially do that, and then you can start to understand why there are so many different types of modules and why people have huge systems. Is that this kind of obsession with changing control voltages in subtle ways over time really adds interest to the sound and creates sounds that are truly unique that you can't actually emulate with other things. So I just wanted to end this on, I guess, a note of remembering the basics and the core concepts. I think this is really important, and this is where it kind of clicked for me, and I started to kind of separate the world of complexity of tons of modules and having choice paralysis and the world of really core basic concepts which are applicable basically across the whole system of modules. Is that, I guess, the two things is remembering to separate audio and control signals. And what I mean is not physically separating them, because oftentimes you can interconnect them, but mentally separating them. So thinking of, you have a series of flows in your system that correspond to how the sound propagates through the system. And then you have another set of system which are basically virtual hands that control different parameters for you over time. And those are the control signals. And the other key concept is just to remember that synthesis is basically the change of the harmonic content or the timbre of the sound. So you're changing volume and frequency. There's only so much you can change of a sound. Every sound is composed of a series of sine waves. So all you're doing is changing the volume of these sine waves over time. And it's really that simple. Now, how you do that is a whole other thing, but I think it's important to remember those key concepts because you can apply them to most other things. And that makes it easier to wrap your hand around some of these concepts, because at the end of the day, each module basically does one or two things really well, and it's the combination of all the modules together that adds the complexity. So in order to remove that complexity, it's helpful to take it step by step and just naturally follow the signal flow and kind of understand what each module contributes to either the audio or the control signal. I'll see you guys in the next one.